Alright guys, I am back for another video installment. So today we are going to be talking about equilibrium. And specifically we're going to be talking about the differences between Ka, Kb, and Kw. Okay, so when we start talking about equilibriums, these are really where the equilibrium starts to become a powerful tool. Because as we've discussed in class, Ka is fine, stoichiometry is fine for strong acids, but for weak acids we really need to worry about equilibria. And since the vast majority of acids are weak, we really do need to start focusing in on how equilibria affects the acids. So we're going to start with Ka first. Now Ka is nice and simple. The A stands for acid. So it's the equilibrium for acids. Okay. Now let's say we have a generic equilibria, so it'll just be, let's say we have an acid. We're going to call it HA, and it's going to react with water, okay, because acids react with water. And of course this is going to be a weak acid. We're assuming this is a weak acid. And so it reacts with water. The H is going to dissociate and go over to the water. So I'm going to have a hydronium ion. It's called a hydronium, an H3O+. And I'm going to have an A-, okay, or the anion of the acid. Well, let's get a couple of terms down. This, as we said, was hydronium. This is called the conjugate base. This is called the conjugate base. Now we're going to talk more about conjugate bases in another video. Today we're just going to kind of focus in on the equilibrium, or the equilibria of weak acids. Alright, so then Ka, if I were to plug this in, the Ka would be the concentration of H3O+. Times the concentration of A-, all over the concentration of HA. Now you might be looking at this equation, you might be thinking that I forgot something. But in actuality, H2O does not fit into our equilibrium because it's a liquid. Remember, we don't worry about pure liquids or pure solids, because concentrations of those can't change. The amount of moles can, but that's more of a stoichiometry thing. The actual concentration of water really can't change very much. It's a pure liquid. So what Ka is doing, it's looking at the product over the reactant, or it's really measuring the amount of dissociation. So the Ka value is going to tell us how much they dissociate, or how much product, how much actual acid, hydronium, a given weak acid will produce. So our strong acids are going to produce only these and have negligible or zero HA, and that's why it's said that they don't have a Ka value, because it would be product over no reactant, and of course we can't have a number over 0. All right, that's an undefined function. So they don't have a Ka value. In actuality, the likelihood that the HA is actually 0 is probably pretty low. They just have I guess you could say, an approaching infinity Ka value, or a gigantic Ka value, if you want to think about it like that. Okay, so that's for acids. Kb, on the other hand, is for bases. So Kb, no shockers for bases. I'm just going to add a little line there to kind of differentiate. Okay, so our dissociation for bases is going to start with a B, because bases aren't acids, so it should start with a B. And it's going to combine with water, H2O. And we're going to, of course, have another equilibrium. And it's going to form, or I'm getting ahead of myself. And H is going to, from the water, is going to go over to the B, and I'm going to be left with HB plus OH-. And that's a positive charge. Okay, so this is the dissociation of a base. I have a base, and it's essentially stripping a hydrogen off the water, forming HB plus an OH-. Okay, so we could say that the Kb value of this is the concentration of the conjugate acid. All right, I forgot to write that. That's the conjugate acid. Okay, so it's the acid formed when a base reacts. Just like this is the conjugate base over here, this is the conjugate acid. And once again, when we talk about acids or bases in that video, we go into a lot more detail with what a conjugate acid and conjugate base are. Okay, so I have my Kb value. It's concentration of HB times the concentration of OH-. I got a little bit ahead of myself. Whoops, my brackets are a little bit inky. Oh, that's just making it much worse. That's not helping at all. There we go. Okay. And then it's over the concentration of B. Remember, H2O is not part of the equilibrium because it's a liquid. Liquids and solids aren't part of my equilibrium. All right, so that's Ka, that's Kb. I'm going to erase my Ka side because it's taking up a lot of space. Now let's talk about Kw. Okay, let's talk about Kw. So we know Ka is for acids, we know Kb is for bases. Well, Kw, probably shouldn't surprise you, is for water. It's the equilibrium for water, and the Kw actually does some kind of cool things. It plays into chemistry a little bit. Okay, so water is naturally, while it's floating around, it's going to once in a while dissociate into H plus and OH minus. Okay, so it just happens. Water will break apart. It's reacting with different things. Some particles will heat up and the bond will break. It's just a natural process. So the Kw value for this is the concentration of H plus times the concentration of OH minus. It's not going to be over anything, however. Because remember, we said that water is a pure liquid and it doesn't take into account on the equilibria, so it's just over 1, or over nothing, if you want to think about it like that. Now, the Kw is a known quantity, Kw. It's actually 1.0 times 10 to the negative 14th. So it's telling you that very, very rarely do I have these concentrations, or rather, I should say that those are in very small concentrations. So when I have a glass of water, only about 1.0 times 10 to the negative 14th of those water molecules break apart. Now, that's a ridiculously tiny amount, but it is important, and it is appreciable. Now, hopefully, some of you guys picked up this number right here, 14. Now, we're talking about acids and bases. 14 is going to become an important number. I'm not going to tell you why, because I don't want to ruin the surprise. Okay, it also turns out that we can do a couple of things with the Kw. Ka times Kb is going to equal my Kw. Okay. Now, Kw is going to play an important role because let's say we have an acidic solution, we dissolve an acid in water. It's important not to forget that some of that water will dissociate. Okay, so when we dissolve an acid in that water is going to play a role. Forever, we've just been ignoring the fact that it's aqueous, but in actuality, the aqueous solution does affect the reaction, because at any given point, we have, let me find it, take a look, we have product in our equilibrium, or we have reactant in that equilibrium. So that is going to play a role. Not a gigantic role, but an appreciable role. Okay, so let's do an example. So I'm going to erase all of this so I have the entire board. All right. Okay, so I've got the whole board to work with. So we're going to do an example of how to utilize the equilibria for weak acids or weak bases. So, what is the pH of a 0.50 molar acetic acid solution, or acetic acid? There we go. We're just gonna, oh boy, erase too much. There we go. Okay, so what is the pH of a 0.50 molar acetic acid? Now, if acetic acid were a strong acid, we could assume that all of it would dissociate, and we could assume that this would be our hydronium, take the negative log of that, wham bam, you're done. That's not the case. Acetic acid's a weak acid. Not 100% of this acetic acid will dissociate. So our hydrogen concentration, or our hydronium concentration, will not be 0.50 molar. Okay, so like I said, not all of this is going to dissociate, so not all of this, our hydrogen concentration, is not going to equal that. So, we have to do a couple of things. First off, we're going to write acetic acid. And we're going to kind of write it, I don't like the way we write it this way, but it's really easy to see that it's an acid, so that's why we're going to do it. It's kind of a funky way to write it. I'm not the biggest fan, but for you guys, I'll write it this way for you, for the students, for learning. Okay, so here's acetic acid. Usually you see it as C2H3OOH or CH3COOH. What I did was I put the H in the front. That way it's easy to realize that that's an acid, because acids have H's in the front. Okay. It's going to react with water, and this H is going to be donated because it's a Bronsted-Lowry acid. It's going to be donated to the H2O. So it's going to form H3O. And it's also going to form the conjugate base of acetic acid, which is C2H3O2 minus. Okay. There's our little diagram. Let me erase this little dotted arrow because that's going to get in our way. Okay. Well, I have an equilibrium. And, oh, sorry, I forgot my K value. I'm going to tell you that Ka equals 1.8 times 10 to the negative fifth. Okay, so I have my equilibrium. I have my equation. I have a Ka value. So it should be very, very obvious what we're going to do. This should be screaming to you. If I have an equation and I know it's an equilibrium, you should be going, I need to ice this. This needs to be an ice diagram. So let's ice it. Okay. Now I have half a molar, 0.50 molar acetic acid to start with. Water doesn't play a role in our equilibrium. It's 0, 0. Okay. All my coefficients are 1, so I'm going to be losing x here, I'm going to be gaining x here, and I'm going to be gaining another x here. So my equilibrium is 0.50 minus x. And here's going to be x and x. Okay. So now I'm going to jump over here, and I'm going to plug this into my Ka. Actually, I'm going to go, how far are you going to go down? I can go down about that far. Perfect. Okay, so Ka is going to equal my reactants over my products over my reactants. Ka is my products over my reactants. Pop over pour. So it's going to be x squared over 0.50 minus x. All right, I know my Ka value is 1.8 times 10 to the negative 5, so I'm just going to plug that in for Ka. 1.8 times 10 to the negative fifth. Now, at this point, probably your best bet is to make an assumption. I have a very small Ka value, so I'm going to assume that it's really not going to play a role in the equation too much. I start with so much acetic acid that the fact that that Ka value is fairly small means that the change isn't going to be that great. In fact, that the change probably wouldn't even notice with sig figs. So that's why we get rid of that x. That cleans up our equation a little bit. It's a whole lot easier. We just solve for x, and we're going to get x, which is equal to the hydrogen concentration, right? Because x is hydronium, hydronium is hydrogen. We're going to get that to equal 3.0 times 10 to the negative third. Now, the reason I specified that it's hydronium or hydrogen is because they want the pH. Okay, this isn't our answer. Our answer isn't 3.0 times 10 to the negative third molar. Our answer needs to be in pH. Well, I know that pH equals the negative log of my hydrogen concentration. I have my hydrogen concentration right here. I can just plug that in and solve on my calculator. And I'm going to get that pH equals 4.52. That is our answer. Okay, so Ka and Kb would be the exact same thing. Of course, you'd have to subtract it from 14 because you'd be finding the POH in this case. But a weak base is the same. So this is how we take an equilibrium, this is how we take an ice diagram and apply it to weak acids. Now, once we get our hydrogen concentration, we can do all kinds of things with that. And weak bases aren't hugely different than, weak acids aren't hugely different than strong acids, but they are different, and we do need to take a couple of things into account. And we'll be working through that in subsequent videos, just like we've been talking about in previous videos. Okay, I hope that really cleared up how to use Ka. If you have any questions, please don't hesitate to ask me. All right, see you in another video.